ever real or relative state interpretation. Remember, basically, what the statistical representation says is don't take the formulas of quantum mechanics seriously, even at the microscopic level, let alone at the macroscopic level. What the many worlds interpretation says, at least as developed by some of its more enthusiastic advocates, is no, quite the opposite. Take the formulas of quantum mechanics deeply seriously, both at the level of electrons and atoms and at the level of cats. So they say, yeah, sure. You should take the formal quantum mechanical description, final state of your cat, very, very seriously. That cat really is, in some sense, neither alive nor dead. In other words, there are parallel universes, in one of which she's alive and the other she's dead. I'll say, wait, look, I just took the lid off this particular box, and this particular cat seems to be alive and sitting up and doing happily. What's happened to the part of the quantum mechanical amplitude which corresponds to the dead? Whereupon the adherents of the many worlds interpretation of the straight in the face and say, well, you have to realise that there is a parallel universe in which not only is this particular cat dead, but you agree that she's dead, and all your colleagues agree that she's dead. And then there are all sorts of formal theorems which says you could never, in some sense, get any interaction between these different so-called parallel universes. Well, I wish I could say something intelligent about that the many worlds interpretation, but alas, I can't. And the reason I can't is that quite literally I do not understand it. I simply do not understand what the words are supposed to mean. I mean, when it's said that these parallel universes, of which I am not conscious and by hypothesis never will be able to be conscious, never could be conscious, and it's said that they are, quote, equally real, unquote, to the one I actually think I observed, these words sound like English. What do they actually mean? I don't think they mean anything at all. And I'm sure I'm going to offend at least some people in the audience at this point, but quite frankly, I believe that when historians of science, in the year 2200, say, look back on this particular period in our history, they will be amazed at how so many otherwise intelligent physicists could embrace this process. So I really don't take this seriously. So that leaves what I call the orthodox resolution. The reason I call it that is that I think it's the kind of resolution that many practicing physicists who've not thought seriously about the foundations of quantum mechanics and at some stage come to think about it, they tend to end up with this kind of solution. You recall that in general, the probability from B or C was not set with the sum of probabilities from B and C. You had this extra interference term. However, you might also recall that if A sub C is equal to plus or minus A sub B at random, then the interference term averages to 0, and you get back to the common sense result. Now, generally speaking, the effect of the outside world is to randomize the sign of A sub C relative to A sub B. Technically, that's a slight oversimplification. I hope the physicists in the audience will forgive me, but crudely speaking, that's right. And this randomization gets more effective as the system gets larger and more complicated and in contact with more of the outside world. And therefore, the general belief which I share is that under most circumstances, when by the time you get up to everyday objects like cats, the interference term has totally vanished. That phenomenon is technically known as deep interference. Now, if the interference term vanishes, that means you get the common sense result. And the common sense result is precisely the one which you would have got if you supposed that each system chooses either B or C. So, at this point, people usually, this step is usually swept under the rug, not stated explicitly, but people say, well, since all experimental results are the same as they would have been, if each cat had been alive, definitely alive, or definitely dead, then we can say each cat was definitely alive or definitely dead. Do you believe that? I think that that argument actually imposes a severe logical fallacy. It confuses the question of the validity or non-validity of a certain interpretation of the quantum mechanical formalism with the evidence that that interpretation is indeed illegitimate or legitimate. At the microscopic level, we concluded that we could not interpret the situation in which both the amplitudes, like the B and C, were non-zero. We could not interpret that as saying each individual atom realized either possibility B, not the possibility C. The evidence against that was the phenomenon of interference. Now, by the time we got up from the level of atoms to the level of cats, everyone agrees that the interference term has gone away. But the formulas of quantum mechanics has not changed one bit in those two stages. So does that mean that just because the evidence has gone away, we can radically reinterpret the meaning of the formulas? I think it's a bit like asking the following question. Suppose we have a murder trial, and there's a vital piece of evidence which everyone says must establish the guilt of the accused. Suppose we killed his wife, say, and the axe with her blood all over it, the bricks all over it. That's an inclusive piece of evidence that he's guilty. Suppose that halfway through the trial, that vital piece of evidence mysteriously disappears. Does that mean the accused has suddenly become innocent? I think it does. Therefore, I don't believe that's simply because the evidence has gone away. You can legitimately, totally reinterpret the meaning of the quantum mechanical theories. So, if you don't find any of these resolutions satisfactory, let's perhaps challenge the assumption which was essential to the resolutions, namely that quantum mechanics is a universal description of the world. Let's make an alternative assumption. Suppose that quantum mechanics breaks down at some point from the atom to the cat. You say, okay, that's a nice qualitative idea. Do we actually have any concrete examples of theories which embody this? And yes, the answer is very simple, actually. The best developed is the so-called Gerardian-Poole theory. In that theory, you have a universal, non-quantum mechanical noise background. It's very crucial that the noise background not be itself described by quantum mechanics, but something like side frames. That noise induces a continuous stochastic evolution of a superposition to one or other of the two states involved. It's triggered by a large, about 10 to the minus 5 centimeters separation of the centre of mass of some number n of particles in the two states. Very crucially, and this is what's interesting, is that this is not an extra assumption. It's built into the whole foundations of the geometry theory. The rate of evolution from a superposition into one or other of its branches is proportional to n. So this means, for example, that you can have a photon which has come from the most distant quasar currently visible in the universe. This photon has been on the road for billions of years. You can put it through the arms of a Michelson interferometer, say, and it will still show the standard quantum mechanical interference effects. Why? Because it's only one particle. So the rate of evolution is very, very slow. Now, on the other hand, consider the possible states of Schrödinger's cat. Certainly, there are a very, very large number of atoms which are behaving totally differently, depending on whether she's alive and well and sitting up and viewing, whether she's stopped over on the floor. So the rate of evolution is something like 10 to the 30th faster than it was for the photon, which means that it's far, far faster than the minimum resolution time in time human observation. So that's a very nice feature. Now, of course, in order the GRWP theory doesn't predict drastically different things from things we've already established. It's got to give its statistical predictions in a typical measurement situation which are identical to those of standard quantum mechanics. And indeed it does. It's constructed to do so. Well, GRWP is the best developed, but there are also theories, for example, based on special effects of gravity. For example, Roger Penrose is constructing such a theory, and one or two others floating around too. I won't be particularly interested in the details of a theory of this type. I'll just define a general class of theories which I call macro-realistic. And crudely speaking, that means that by the time you get to the level of pointers and cats and similar everyday objects, you can't have a quantum superposition of two different states. Everything has to do one thing or the other, just as we've already seen in everyday life. Well, given these two possibilities, the obvious question is quantum mechanics in fact the whole truth? How will we tell? Well, I think you can fairly easily see that if all everyday objects have the property that the interference term is randomized, in other words, you have complete decoherence, then you will always get common sense results. That is, all experimental results will be exactly as if each system following one path or the other. So in that case, one can't tell whether quantum mechanics is the whole truth or not. So we better try to find some everyday scalar object where decoherence is not effective. And the question is, does any such object exist? Well, there are several essential properties it must have. First of all, the difference of the two states in question must be at the everyday level. However, the relevant energies which drive the dynamics, as it were, must be at the atomic level. Now, you might think at first sight these two requirements are mutually contradictory, but it turns out not. There are quite a number of systems which do actually satisfy this, and we'll see one of them in a moment. You must have, in order to avoid decoherence, you must have, first of all, an extreme degree of isolation from the outside world, and secondly, very low intrinsic participation. Well, there are such systems, and so come in a moment, but how do we approach this problem? Well, obviously, if we're going to tell whether quantum mechanics is right or not, you've got to be able to do quantum mechanical calculations. And these are hard, because you're dealing, generally speaking, with very complex macroscopic objects, and while it's tempting to base everything on a priori microscopic description, it simply isn't feasible in most cases. You just don't know enough about the system to give a complete microscopic description. So that's not a good way to go. Rather, what one can try to do, people have tried to do in the last 30 years or so, is to study the experimental behaviour in the classical limit, that is the limit where everyone agrees that quantum mechanics, quantum mechanics are basically reduced to those classical mechanics. From that experimental behaviour, you try to derive enough about the microscopic description,